Thanks for attending this talk. My name is Udit, and I'm a fourth-year PhD student at Harvard University, and today I will be presenting our work on DeepRecSys, a system for optimizing end-to-end ASCA neural recommendation inference. Personalized recommendation is a task of recommending new content to users based on their personal preferences. We start with a large set of candidate items that could be served to the user. These items are then ranked with deep learning-based recommendation models. And finally, the top few items are then served to the user. These recommendation systems are run at a tremendous scale in data centers. For instance, production scale recommendation systems must meet strict SLA targets while ranking hundreds of thousands of items with large scale models with billions of parameters serving billions of users worldwide. Because of the scale, recent work shows that recommendation accounts for over 80% of all AI inference cycles in Facebook's data centers. As a result, it is crucial to improve the efficiency of neural recommendation inference. However, we find significant heterogeneity across recommendation use cases, which requires automated tools and flexible systems for optimizing this key workload. First, recommendation models are deployed across many use cases, such as social media, search, e-commerce, and entertainment. Each of these use cases has a different SLA target to preserve QoS and the user's experience. Furthermore, we find each use case leverages a different type of recommendation model with unique performance characteristics. Second, in addition to the diversity across use cases, we see a rapid evolution of recommendation models being used. Here on the y-axis, we see the number of unique recommendation model training workflows, which has increased by a factor of 7x over just 18 months in Facebook's data center. This increase demonstrates that recommendation models significantly evolve over time, and new ones are always on the horizon. Third, and finally, in addition to the algorithmic diversity, we see significant hardware heterogeneity in the data center. Data centers not only comprise various types of server-class CPUs with different microarchitectural features, but due to the Cambrian explosion of specialized hardware, also comprise many different types of AI accelerators. Given the scale of recommendation in production data centers, it is crucial to design solutions that can enable efficiently using all available hardware resources for recommendation inference. However, when we look at this space, we find a lack of tools to study solutions that can exploit the unique characteristics of this workload and efficiently deploy a variety of recommendation models with different SLA targets across heterogeneous hardware. To address this gap, in this talk, we propose DeepRecSys, the first infrastructure and scheduler to optimize the runtime performance of end-to-end ASCA neural recommendation inference. The key challenge we address is how to optimize the performance of recommendation across various heterogeneous hardware available in the data center. To address this challenge, we first understand the massive design space encompassing different models, hardware platforms, and unique input query characteristics. Next, we design infrastructure to quantify the impact of each key component of the design space, including the models, hardware, and query characteristics. Next, we use the infrastructure to design a scheduler to optimize the inference performance across diverse recommendation use cases and heterogeneous hardware. We identify that the key optimization metric is to maximize the number of queries processed per second under strict latency targets. To maximize this latency-bounded throughput, we designed a batch scheduler that can parallelize queries across both CPUs and accelerators. Finally, we measure the benefits the scheduler provides for deploying recommendation at the data center scale. Our experiments demonstrated 2x performance improvement on CPUs and 5x in the presence of accelerators. To maximize power efficiency, we find that the optimal hardware platform varies across the different recommendation use cases. And finally, when we deploy the scheduler in a real production data center, we measure a 30% performance improvement with real shadow traffic. First, let's look at this overall design space. We start by looking at the diverse collection of neural recommendation models. Recommendation models have two types of inputs. First are continuous inputs that are processed with a set of DNN layers. The second are categorical input features that are represented as multi-hot encoded vectors. Now, given the scale of internet services that use recommendation models, these vectors are not only large, but also incredibly sparse. One way to transform these sparse inputs into dense ones is to use embedding tables. Entries of the multi-hot encoded vectors are used to index rows within the tables to read low-dimensional embedding vectors. These vectors are then pooled together and combined with the output of dense DNN stacks. Finally, a predictor DNN stack outputs the probability of users interacting with the items. Now note that by configuring 3 key components of the network, we can realize different implementations of recommendation models. First, the compute intensity of the model can be set based on the depth and width of the dense DNN layers. Second, the memory intensity of the model can be set by the number of unique embedding tables and number of lookups per table. In fact, in production scale models, we find that these embedding tables consume tens of gigabytes of storage and have highly irregular memory access patterns, making hardware acceleration quite challenging. And third, the operators used in feature interaction determine the communication pattern within the network. Here we look at how configuring these components can realize distinctly different types of networks. First, we look at embedding dominated models. These are characterized with having tens of embedding tables, each of which has tens or hundreds of lookups per table, as highlighted in blue here. Another class of recommendation models were once dominated by MLP layers. These typically have one hot encoded lookups per table with large MLP layers and sometimes even multiple output predictor DNN stacks. Lastly, we have attention-dominated models with one hot encoded lookups and complex feature interaction layers that are highlighted in green here. In particular, we often find complex attention or sequential modeling techniques such as recurrent layers are used within the feature interaction components of these networks. Now note that all 3 types of recommendation models are used across various internet services such as social media, search, e-commerce, and entertainment. Next, we will look at specific implementation of these types of models across Facebook, Google, and Alibaba's data centers. Here we're looking at the performance characteristics of 8 industry representative recommendation models on the x-axis and the operator breakdown on the y-axis. As expected, across the different types of recommendation models, we find a diverse set of operator breakdowns. This imposes a diverse collection of system bottlenecks that must be collectively optimized for improving performance of recommendation inference at the data center scale. In fact, while here we consider a single query size of 64, we find that the design space increases with a wider array of query sizes. Here we consider what the range of realistic query sizes are for at-scale neural recommendation inference. Recall that this is the overall recommendation inference process. In particular, the size of the input queries relates to the total number of candidate items to be ranked. To understand the range, we profile the number of candidate items for query sizes in a production data center. On the x-axis, we have the query sizes, and on the y-axis, we have frequency. We find that the majority of recommendation queries are between 100 and 200. At the same time, there exists a heavy tail of query sizes that goes all the way up to 1,000 items per query. Typically, working set sizes in many data center services have a fixed value or follow a normal distribution. Here we overlay a log normal distribution, typically understood to have a long tail in the context of data center services. In comparison, the query sizes for at-scale recommendation inference have a much heavier tail. Note that the larger queries, which typically require more work, are often the ones that limit the achievable system throughput on the strict latency targets. As a result, the heavy tail distribution is crucial for system design and can expose new opportunities for optimization. One interesting question here to ask is at which point should the throughput limiting queries be offloaded to specialized accelerators? Now, in the context of hardware acceleration, we see that there's a Cambrian explosion of specialized AI hardware. At the data center scale, there are proposals for AI hardware spanning GPUs, TPUs, FPGAs, and ASICs. To look at the trade-offs between processing queries on CPUs and accelerators, in this talk, we use an NVIDIA 1080 Ti GPU to model the presence of an AI accelerator. But as we will see later on, the proposed scheduler can adapt to new resources as well. To gain intuition on the trade-off, we look at the speedup of the GPU over a server-class Intel Skylake processor on the y-axis for an embedding MLP and 2 attention-dominated models on the x-axis. First, we consider running the models with a unit batch size, where we find the CPU runs significantly faster than the GPU. This is a result of data communication over PCIe dominating the runtime at lower query sizes. Next, we consider the performance of the models with the largest query size of 1024, where we see the GPU outperforms the CPU across all the different models. While the amount of speedup varies across the models, compute-intensive MLP models achieve the highest speedup with nearly 7x. Finally, here we consider the query size at which both platforms have equal performance. This is crucial as beyond this query size, it is advantageous to process the inference query on the GPU as opposed to the CPU. In the case of embedding an MLP-dominant models, this happens at a batch size of 47 and 23. Interestingly, the inflection point at which the GPUs begin to outperform the CPU for the attention models are 101 and 512, significantly higher than the MLP and embedding dominated models. Now, this characterization shows that processing all queries exclusively on the CPU or exclusively on the GPU is suboptimal. In fact, the optimum hardware platform in which to process the queries depends on the model architecture and the size of the query itself. To optimize over the design space, we first build a scalable infrastructure to model the data center scale recommendation and quantify the impact of models, hardware, and query characteristics. The infrastructure first implements a load generator that samples query arrival and size distribution based on characterizations of production data centers. The load generator then produces queries that the scheduler determines how to process in order to maximize latency-bounded throughput. For example, if the query is sufficiently large, the scheduler will send the query to be run on the accelerator. Otherwise, if the queries are smaller, the scheduler will split them across many CPU cores. Finally, these queries are processed by a variety of neural recommendation models running on these hardware platforms. Now, given this infrastructure, DeepRecSched can be used to study a wide variety of recommendation use cases. For instance, here we're highlighting each key component of the infrastructure that can be extended. The load generator can be extended to look at different input query patterns. The collection of models can be extended to analyze and optimize ones with different performance bottlenecks. And finally, the models can run on a variety of real hardware systems, including general purpose CPUs or real and emulated accelerators. For the remainder of this talk and the results shown in the paper, we instrument DeepRecSys based on our characterization of data center scale recommendation. For instance, the application input queries follow a Poisson arrival rate, and the working set sizes follow the production query size distribution that we saw earlier. We study all 8 industry representative models implemented in Caffe 2. We run the end-to-end system on Intel Broadwell and Skylake CPUs and model the presence of an accelerator with an NVIDIA 1080 Ti GPU. We also consider varying SLA targets by setting a median P95 tail latency target based on open publications. The higher target is 50% longer, while lower targets are 50% shorter. To demonstrate the efficacy of the proposed scheduler, we also deployed the scheduler in a production data center with A/B tests running real shadow traffic over 24 hours. Given the design space made available with DeepRecSys, we find that recommendation inference is optimized in order to maximize the number of queries ranked per second under a strict tail latency target, or latency-bounded throughput. We design and implement a flexible batch scheduler that parallelizes query processing over server-class CPUs and accelerators. First, we consider the parallelism opportunities of the scheduler by splitting individual queries to be processed across multiple cores in the server-class CPUs. Here we see an example of the scheduler processing a query of size 1024. If the scheduler determines a per-core query size to be 1024 as well, this means the entire query is processed on a single core with high data level parallelism, but low thread level parallelism. Alternatively, the scheduler could set a per-core query size of 512 to split the query over 2 cores. Or with a per-core query size of 256, the query is processed over 4 cores with higher thread level parallelism and lower data level parallelism. Here we consider the performance implication of varying per-core query size on the achievable QPS under a strict latency target. On the far right of the x-axis, a query size of 1024 refers to processing all queries on a single core. On the left, queries are split over many cores. Here we consider the performance of an embedding dominated model with varying query sizes and a 100 millisecond SLA target. We find that the optimum per-core query size is 512. Smaller query sizes incur heavier queuing delays, while larger ones have longer latencies, limiting the maximum QPS achievable. Analyzing the MLP-dominant model and the attention-dominant model, we find the inference QPS is maximized at unique per-core query sizes for each model. In fact, in the paper, we find the optimum point varies not only across models, but also across SLA targets that encompass the various recommendation use cases. Given this diversity, an automated solution framework is needed to find the optimum batching configurations across the different use cases. Thankfully, based on the characterization we see here, we find a hill climbing based scheduler can automatically find the optimum per core query size. In fact, in the paper, we show that this hill climbing based scheduler flexibly optimizes latency bounded throughput on CPUs across different recommendation use cases with varying model architectures and SLA targets. In addition to balancing parallelism across cores, the scheduler can also offload queries to an accelerator. Recall the heavy tail distribution of query sizes found in Facebook's production data centers. The intuition here is to offload larger queries above a specific threshold to the accelerator. Here we measure the impact of tuning this threshold to offload queries to the GPU on inference QPS. We find the optimum query size threshold is 180 for the MLP-dominated model. Queries of smaller size found to the left of the threshold are processed on the CPU. Queries of larger sizes are processed on the accelerator. A higher threshold would not sufficiently exploit the accelerator's capabilities, while lower ones would offload too much work to the accelerator and thus incur heavy queuing delays. Now recall the inflection point of when the GPU outperforms a standalone CPU is lower than the optimum query size threshold. This highlights the importance of studying the distinct query size distribution found in production workloads. That is, systems must optimize across a unique distribution for at-scale recommendation. We find this holds true for embedding-dominated and attention-dominated models as well. Furthermore, we find that the optimum threshold varies across the different model architectures. Now, more generally, we find that the proposed scheduler with the hill climbing based implementation can flexibly optimize inference QPS on both CPUs and accelerator platforms across the varying model architectures, unique application load characteristics, and varying SLA targets. Now, finally, we measure the improvement the scheduler provides for deploying at-scale recommendation in the data centers. Here we consider the performance implication of DeepRecSched compared to a static batch scheduler based on Facebook's production data center. Intuitively, the static scheduler coarsely optimizes for a handful of models based on hand-tuning batching configurations to parallelize the largest query across all available CPU cores. Compared to this static scheduler, we find that DeepRecSched improves system throughput by 6x on embedding-dominated models and nearly 3x on attention-dominated models. In the presence of accelerators, DeepRecSched also improves the performance of the compute-intensive MLP models by nearly 4x. Now note that despite the additional hardware, the embedding and attention-dominant models have limited performance improvement. Given this limited speedup, we actually find that in terms of power efficiency, the accelerator-enabled nodes are not always optimal. For example, while the GPU-based accelerator improves the power efficiency in terms of QPS per watt by nearly 2x for the MLP-dominated models, it degrades efficiency by 1.25x for the embedding-dominated and nearly 2x for attention-dominated models. As a result, while scheduling queries across both CPUs and accelerators is optimal for performance, power efficiency depends on the model type. Now, in addition to the evaluation on top of the proposed infrastructure, the paper also details the scheduler's performance when deployed in a real production data center. Now, in the interest of time, we won't go into detail, but only mention that the proposed scheduler improves performance by nearly 30% on real shadow traffic. Furthermore, the paper provides details such as the scheduler's performance across varying query arrival rates and size distributions. We also provide details on the impact of microarchitectural features such as SIMD width, cache capacity, and clock frequency on recommendation inference and the scheduler's decisions. And finally, in the paper, we show deeper results on the performance of the accelerator systems on varying SLA targets and the impact of more power-efficient systems on scheduling and data center provisioning. In conclusion, in this talk, we first highlight the massive design space encompassed by recommendation, including the diverse set of models SLA targets, and application load characteristics. Next, we propose a scheduler to parallelize queries and optimize at-scale performance by 2x on CPUs and 5x in the presence of GPU-based accelerators across a wide design space. And finally, if you are interested in this work, we have recently open sourced a developed infrastructure, including the industry representative models and recommendation load generator. The open source infrastructure could be used to optimize new models, propose new scheduler designs, and quantify the benefits of new accelerators. We will detail how to run and use the infrastructure during the personal tutorial held in conjunction with ISCA. And with that, I will conclude this talk. Thank you for listening.